Deep within the circuits and components that power our modern world, there exists a phenomenon so subtle, so quiet, that it can go unnoticed for years. Yet when it reveals itself, the consequences can be catastrophic. We're talking about metal whiskers, tiny, crystalline structures that grow spontaneously from the very surfaces designed to conduct electricity and hold our devices together. Metal whiskers are hair-like crystalline filaments that emerge from metal surfaces used in electronic hardware. They appear most commonly on electroplated finishes, those smooth, protective coatings applied to countless electronic components. These whiskers don't announce their arrival. They don't send warning signals. They simply grow, silently and steadily, deep within the heart of electronics. Imagine something so small that it exists at the very edge of what we can perceive. Individual tin whiskers are typically only about 1 to 10 micrometers in diameter. To put that in perspective, a single human hair is roughly 70 micrometers across. These whiskers are many times thinner than that. And yet, despite their incredibly slender profile, they possess an unsettling ability to reach out across space. They can grow to lengths of several millimeters, and in some documented cases, they've been found stretching up to about 10 millimeters long. That's a full centimeter of crystalline growth, emerging from a surface that should, by all appearances, remain stable and unchanging. When we think about problematic metals in electronics, tin immediately comes to mind, and for good reason. Tin is the most notorious whisker-forming metal we know of. It's used extensively in the electronics industry for plating and soldering, precisely because of its excellent conductivity and corrosion resistance. But this useful metal harbors a secret tendency, a propensity to sprout these microscopic filaments under the right conditions. However, tin is not alone in this behavior. Whiskers can also grow from zinc, cadmium, silver, indium, antimony, aluminum, and even gold surfaces. Yes, even precious metals aren't immune. And interestingly, even lead, which was once commonly used in solder formulations, can develop whiskers, though it does so far less readily than tin. What makes whiskers particularly unsettling is their stealth. These structures often grow slowly, developing over the course of months or even years. They're nearly invisible without magnification. You could hold a circuit board in your hand, examine it closely with the naked eye, and never know that whiskers are forming, reaching out toward neighboring components, creeping ever closer to creating an electrical bridge. They can remain completely undetected until the moment they trigger a sudden, catastrophic failure. One moment, a device is functioning perfectly. The next, a short circuit occurs, and the mystery begins. Now, you might think that whiskers would require certain environmental conditions to grow, perhaps moisture, or contaminants, or some chemical reaction. After all, many forms of metal degradation do require such elements. Corrosion dendrites, for instance, those branching, tree-like structures that can form on circuit boards, typically require humidity and contamination to develop. But metal whiskers are different. They grow spontaneously in dry, clean environments. They don't need moisture. They don't need dirt or chemical residues. They simply grow. This makes them particularly insidious in environments where engineers have taken great care to protect electronics from traditional forms of degradation. Consider for a moment the extraordinary measures taken to protect sensitive electronics. Components are often hermetically sealed, enclosed in airtight packages designed to keep out moisture, dust, and contaminants. Other assemblies receive conformal coatings, thin protective layers applied to circuit boards to shield them from environmental threats. These measures are highly effective against most forms of degradation. But whiskers can grow even in hermetically sealed or conformally coated assemblies. The seal that keeps out moisture cannot stop a crystalline structure from growing from within. The coating that protects against contamination cannot prevent metal atoms from rearranging themselves and pushing outward from a plated surface. When we discuss whisker growth, it's important to understand that this isn't a phenomenon limited to one particular type of component or one specific location within an electronic assembly. Whisker growth is not limited to solder joints, though those are certainly vulnerable. It also occurs on connector pins, those small metal contacts that allow different parts of a system to communicate. It happens on relay terminals, where electrical signals are switched on and off. It affects component leads, the thin metal legs that connect integrated circuits to circuit boards. And it even appears on shields, the metal enclosures meant to protect sensitive circuits from electromagnetic interference. Anywhere electroplated metal exists, whiskers can potentially form. Another deeply unsettling aspect of whisker formation is that it doesn't discriminate between active and inactive equipment. Whiskers can grow in both powered and unpowered equipment. You might assume that electrical current flowing through a circuit might influence whisker growth, either promoting it or perhaps inhibiting it. But the reality is that whiskers develop regardless of whether electricity is flowing. This means they can form in dormant spares, equipment that's been carefully stored away, waiting to be deployed when needed. Imagine opening a sealed container of replacement circuit boards that have been in storage for years, only to discover that whiskers have been growing silently in the darkness, potentially compromising the very components you were counting on as backups. Perhaps the most frustrating characteristic of whisker-related failures is their unpredictability. The time to failure due to whiskers is highly unpredictable. Two identical components, manufactured in the same batch, installed in identical environments, can behave completely differently. One might develop problematic whiskers within months, while the other might operate for decades without issue. This unpredictability makes it extraordinarily difficult to plan maintenance schedules or predict when replacements might be necessary. It introduces an element of randomness into systems that engineers strive to make deterministic and reliable. Research has shown that tin whisker incubation periods, the time between when a component is manufactured and when visible growth begins, typically range from 100 to 10,000 hours. Let's think about what that means. At the short end, 100 hours is just over 4 days. At the long end, 10,000 hours represents more than a year of continuous time. This enormous range reflects the complex interplay of factors that influence whisker growth. Temperature fluctuations, mechanical stress, the exact composition and thickness of metal plating, the properties of underlying substrates. All of these variables and more can affect when and whether whiskers will begin to grow. And so we find ourselves confronting an invisible threat, one that exists at a scale far too small for our eyes to perceive directly, yet large enough to bridge the microscopic gaps between conductors in our most sophisticated electronics. Metal whiskers represent a reminder that even in our age of precision manufacturing and advanced materials science, nature still finds ways to surprise us, to introduce chaos into our carefully ordered systems. They grow in silence, in darkness, in sealed containers and coated surfaces, patiently extending themselves until they find a target, or until someone, somewhere, discovers them first. In the segments to come, we'll explore the mechanisms behind this phenomenon, the catastrophic failures it has caused, and the ongoing efforts to understand and mitigate this microscopic menace. But for now, simply knowing that these structures exist, that they're forming right now in electronics all around us, that's enough to contemplate as we continue our journey into the hidden world of metal whiskers. The story of metal whiskers is not a recent discovery. It's not something that emerged with modern electronics or contemporary manufacturing techniques. No, this phenomenon has been quietly plaguing engineers and technicians for the better part of a century, leaving behind a trail of mysterious failures and perplexing malfunctions that took years to understand. Historical records document tin whisker failures dating back to the 1940s, found in vacuum tube relays. Think about that for a moment. We're talking about technology from the era of World War II, when electronics were still in their relative infancy, when vacuum tubes were the cutting edge of amplification and switching technology. Even then, even in those early days of electronic engineering, whiskers were growing. Relay contacts, those critical switches that opened and closed electrical circuits, would mysteriously fail. Engineers would investigate, sometimes finding nothing obviously wrong, other times discovering these strange, hair-like structures bridging gaps that should have remained insulated. At the time, the understanding of what these structures were and why they formed was limited. They were curiosities, anomalies, problems to be solved on a case-by-case basis. As we moved into the 1950s, the telecommunications industry was expanding rapidly. Telephone exchanges, those massive installations of switching equipment that connected calls across cities and countries, represented some of the most complex electronic systems of their time. And they too fell victim to whiskers. Historical vacuum tube failures in 1950s telephone exchanges involved silver whiskers bridging grid cathode spacings. Silver, that precious metal prized for its conductivity, was sprouting crystalline filaments inside vacuum tubes. The grid and cathode in a vacuum tube must maintain precise separation to function correctly. When a silver whisker bridged that gap, it created a short circuit, causing the tube to malfunction. Imagine the frustration of telephone technicians trying to diagnose intermittent failures in exchanges serving thousands of customers, only to discover that the culprit was a microscopic strand of metal that hadn't existed when the equipment was installed. The space age brought its own whisker-related disasters. In 1964, the Centaur rocket upper stage, a crucial component of America's space program, experienced failures that threatened critical missions. Investigation revealed that cadmium whiskers were shorting telemetry harnesses. Cadmium, often used in electroplating for its corrosion resistance, was forming whiskers that created electrical bridges in the rocket's telemetry systems. The very systems designed to send data back to ground control about the rocket's performance and status. The consequences of such failures in spaceflight are profound. When you cannot receive telemetry, you're essentially flying blind, unable to monitor the health of your spacecraft or make informed decisions about mission continuation or abort procedures. In military applications, where reliability is paramount and failure can mean the difference between mission success and catastrophic loss, whiskers revealed themselves in particularly dramatic fashion. Legacy military RF hardware, radio frequency equipment used for communications and radar, experienced what came to be known as whisker storms, events where thousands of whiskers grew simultaneously. Imagine opening up a piece of radio equipment that had been in service for years and finding not just one or two whiskers, but thousands of them, a forest of metallic filaments sprouting from plated surfaces throughout the assembly. These whisker storms could create multiple failure points simultaneously, overwhelming redundancy measures and bringing down entire systems. The 1980s brought another wave of whisker-induced failures, this time in military radar systems. Legacy capacitor end caps with pure tin terminations failed en masse in 1980s military radar systems. Capacitors are fundamental components in electronics, storing and releasing electrical charge to filter signals and stabilize power supplies. The end caps, those metal terminals where wires connect to capacitors, were electroplated with pure tin. And that pure tin, over years of service, began to grow whiskers. Not just in one capacitor, but across entire production batches. The failures weren't isolated incidents. They were widespread, systematic problems that forced military logistics teams to track down and replace affected components across numerous installations. As we approached the turn of the millennium, whisker failures moved beyond terrestrial systems and into orbit. Tin whisker failures contributed to the 1998 Galaxy 4 satellite loss of control. Galaxy 4 was a communications satellite serving millions of pages across the United States. When it failed, the impact was immediate and widespread. Doctors couldn't be reached. Emergency services lost a critical communication link. The business sector, heavily reliant on pages at the time, found itself suddenly cut off. While multiple factors contributed to the satellite's failure, tin whiskers were identified as playing a role in the cascade of problems that led to loss of control. A satellite that cost hundreds of millions of dollars, orbiting more than 20,000 miles above Earth, brought down in part by crystalline structures measuring mere micrometers in diameter. The phenomenon gained widespread attention after the 2003 NORAD missile control system outage. NORAD, the North American Aerospace Defense Command, maintains constant vigilance over North American airspace, tracking potential threats and coordinating defense responses. When their missile control systems experienced an outage, it wasn't just a technical inconvenience, it was a national security concern. Investigation traced the problem to tin whiskers. The incident served as a wake-up call for the defense and aerospace industries, forcing a broad recognition that whisker formation was not just an occasional nuisance, but a systemic threat to critical infrastructure. In response to decades of whisker-related failures, NASA, the agency perhaps most acutely aware of the consequences of electronic failure, took action. NASA maintains an extensive tin whisker database tracking confirmed failures since the 1960s. This database represents an invaluable resource for researchers and engineers, documenting failure modes, affected components, environmental conditions, and timelines. It's a sobering archive, a catalogue of incidents where microscopic metal growth created macroscopic problems. The database continues to grow, with new entries added as failures are investigated and whiskers identified as contributing factors. Whisker failures haven't been limited to aerospace and defense applications. The medical device industry has also grappled with this threat. The FDA, the Food and Drug Administration responsible for ensuring the safety and efficacy of medical devices, has documented tin whisker failures in medical devices like pacemakers and insulin pumps. Consider the implications. A pacemaker maintains a patient's heart rhythm, delivering precisely timed electrical pulses that can mean the difference between life and death. An insulin pump delivers carefully measured doses of insulin to manage blood sugar in diabetic patients. When these devices fail due to whisker-induced short circuits, the consequences are immediate and potentially fatal. The FDA's documentation of these failures underscores the breadth of the whisker problem. It's not just about satellites and missiles, but about everyday devices that people depend on for their very survival. Even modern infrastructure has proven vulnerable. Zinc whiskers from galvanized steel have caused multiple data center outages. Data centers, those vast warehouses filled with servers that power our cloud services, websites, and digital communications, often use galvanized steel in their construction, particularly for raised floor systems and HVAC components. Galvanization involves coating steel with zinc to prevent rust. But that zinc, under certain conditions, grows whiskers. These whiskers can break free from their parent surfaces and become airborne, drifting through data center environments until they settle on circuit boards or are drawn into ventilation systems. Once there, they can create short circuits in servers and networking equipment, bringing down systems that serve thousands or even millions of users. The historical record of whisker failures paints a picture of a problem that has persisted across decades, across industries, across applications from the most mundane to the most critical. Each failure taught lessons, sometimes at enormous cost. Each investigation added to our understanding of how whiskers form, where they appear, and what conditions promote their growth. But despite decades of awareness, despite extensive research and documentation, metal whiskers continue to form, continue to cause failures, continue to lurk within electronics as an invisible, unpredictable threat. As we continue our exploration of metal whiskers, we'll delve deeper into the science behind their formation, the mechanisms that drive their growth, and the ongoing efforts to predict and prevent them. But this historical perspective is crucial because it reminds us that this is not a theoretical problem or an academic curiosity. It's a real, persistent challenge that has been quietly undermining the reliability of electronics since before many of us were born, and it shows no signs of going away. To understand why metal whiskers command such concern from engineers across industries, we need to examine what happens when these microscopic structures interact with the electrical systems they inhabit. The danger isn't merely theoretical. It's immediate, tangible, and in some cases explosive. At the most fundamental level, metal whiskers can cause hard electrical shorts between adjacent conductors. A hard short is exactly what it sounds like, a direct, unintended electrical connection between two points that should remain isolated from each other. In electronic circuits, conductors often run parallel to each other, separated by distances measured in fractions of a millimeter. These narrow gaps are carefully designed to prevent electrical leakage while maximizing the density of components on a circuit board. But when a whisker grows from one conductor and reaches across that gap to touch another, it creates a bridge. Current that should flow along one path suddenly has an alternate route. Voltages that should remain distinct become equalized. The circuit no longer functions as designed. In some cases, the result is merely a malfunction. In others, it's a cascading failure that takes down entire systems. But whisker-induced damage extends beyond simple short circuits. Even when they do not create direct shorts, whiskers can interfere with MEMS and optical components. MEMS, microelectromechanical systems, are tiny devices that combine mechanical and electrical elements at microscopic scales. They include accelerometers in smartphones, pressure sensors in automotive systems, and gyroscopes in navigation equipment. These devices rely on precisely controlled mechanical movements, tiny cantilevers, membranes, or proof masses that move in response to physical forces. A whisker growing near or into a MEMS device can physically obstruct these movements, causing sensors to malfunction or provide false readings. Similarly, optical components, devices that manipulate light for communications or sensing, require unobstructed light paths and precisely positioned elements. A whisker growing into an optical path can scatter light, reduce signal strength, or completely block transmission. When we examine the electrical properties of whiskers themselves, we find that they're remarkably efficient conductors. Tin whiskers exhibit electrical resistivity similar to bulk tin. This means that a whisker isn't a poor conductor or a semi-insulating structure that might limit current flow. No, it conducts electricity almost as well as a solid chunk of tin metal. Given that whiskers are essentially single crystals or highly ordered crystalline structures, this high conductivity makes sense. There are fewer grain boundaries and defects to impede electron flow than you might find in polycrystalline bulk metal. The practical implication is that when a whisker creates a bridge between conductors, it's not a high-resistance connection that might self-limit the fault. It's a low-resistance pathway that allows substantial current to flow. And substantial current can indeed flow through these delicate-looking structures. Whiskers can carry currents exceeding 100 milliamperes before fusing. 100 milliamperes might not sound like much, but in the context of sensitive electronics, it's enormous. Many integrated circuits operate with currents measured in microamperes or milliamperes. 100 milliampere fault current is more than enough to damage components, corrupt data, or trigger protective circuits that shut down systems. The fact that whiskers can sustain such currents before they physically fail speaks to their structural integrity. They're not fragile strands that immediately vaporize when current flows. They're robust enough to conduct damaging levels of current for extended periods. What happens when that current finally does exceed the whisker's capacity? Under certain conditions, a whisker-induced short can vaporize into a metal plasma. Imagine the sequence of events. Current flows through the whisker, heating it through resistive losses. The temperature rises rapidly. The whisker begins to glow. And then, in an instant, it transforms from solid metal into a plasma, a state of matter where atoms are ionized, where electrons are stripped away, where the material becomes a hot, conductive gas. This isn't a gentle failure mode. It's violent and energetic. Once formed, these plasma arcs take on a life of their own. Whisker-induced plasma arcs can carry very high currents. The plasma, despite being a gas, remains highly conductive. In fact, once established, a plasma arc can be more conductive than the original solid whisker. Current rushes through the ionized channel, limited only by the impedance of the surrounding circuit. The arc generates intense heat and light, potentially damaging nearby components through thermal stress or radiation. The destructive potential of these plasma arcs becomes even more severe in certain environments. Whisker-induced plasma arcs sustain currents up to 50 amperes in low-pressure environments. Low-pressure environments are common in aerospace applications. Satellites operate in the near vacuum of space, and high-altitude aircraft experience significantly reduced atmospheric pressure. In these conditions, the lack of surrounding air means there's less cooling, less quenching of the arc. Once initiated, the plasma can persist, conducting enormous currents. 50 amperes is enough to weld metal, melt components, and cause catastrophic damage to electrical systems. A tiny whisker, micrometers in diameter, becomes the trigger for an arc that draws more current than many household appliances. The danger escalates further in energy storage systems. Whiskers on battery terminals have triggered thermal runaway in lithium cells. Lithium-ion batteries store enormous amounts of energy in compact packages. They're also sensitive to abuse conditions. When a whisker creates a short circuit across battery terminals, it allows the battery to discharge rapidly, often through an unintended path. This rapid discharge generates heat. The heat accelerates chemical reactions within the battery. Those reactions generate more heat, which further accelerates the reactions. This positive feedback loop is thermal runaway, a self-sustaining process that can result in the battery catching fire or exploding. Modern battery management systems include protections against some fault conditions, but a whisker-induced short can bypass these protections or develop so gradually that protective circuits don't recognize the fault until it's too late. Whiskers don't discriminate by voltage level. While we often think of electronics as low-voltage systems, power distribution equipment operates at much higher voltages, and whiskers threaten these systems too. Aluminum whiskers have bridged high-voltage bus bars in power systems. Bus bars are thick metal conductors used to distribute electrical power in substations, industrial facilities, and large buildings. They may carry hundreds or even thousands of volts. The gaps between bus bars are carefully maintained to prevent arcing, but aluminum whiskers, given enough time, can span these gaps. When a whisker bridges a high-voltage bus bar, the resulting arc can carry enough energy to vaporize metal, create pressure waves, and pose serious risks to equipment and personnel. Power system faults of this nature can cascade, taking down entire sections of electrical grids. Transportation infrastructure has also suffered whisker-induced failures. Zinc whiskers on relay contacts caused railway signaling failures. Railway signaling systems are safety-critical applications where failures can result in collisions, derailments, or other catastrophic incidents. These systems rely on relays, electromagnetic switches that control track signals, switch points, and crossing gates. The relay contacts, often zinc-plated for corrosion resistance, are precisely the kind of environment where whiskers can grow. When a whisker bridges relay contacts that should be open, it creates a phantom circuit closure. Signals may incorrectly indicate that a track section is occupied when it's not, or unoccupied when it is. Switches may fail to change position when commanded. The result is confusion, delays, and potentially dangerous situations where trains operate based on incorrect information. The common thread running through all these failure modes is the disproportionate impact of whiskers relative to their size. Something measuring micrometers in diameter, something you couldn't see without magnification, something that grows silently and gradually over months or years. This tiny structure can bring down satellites, trigger battery fires, disable power systems, and compromise safety-critical infrastructure. The whisker itself isn't inherently dangerous. It's a passive structure, simply crystalline metal. But in the electrical environment of modern systems, where conductors are packed closely together, where voltages and currents are carefully controlled, where margins for error are narrow, in that environment, a whisker becomes a catastrophe waiting to happen. As we continue exploring the world of metal whiskers, we'll examine the physical mechanisms that drive their growth, the specific conditions that promote or inhibit their formation, and the strategies engineers have developed to combat them. But first, it's essential to appreciate the genuine threat they pose. These aren't just academic concerns or minor annoyances. They're real dangers with documented consequences, failures that have cost billions of dollars, compromised critical systems, and in some cases, threatened human lives. Understanding why whiskers are dangerous is the first step toward taking them seriously, and toward developing effective strategies to manage the risk they represent. To truly grasp the whisker phenomenon, we need to descend to the atomic scale, to understand the microscopic mechanics that transform a smooth metal surface into a bristling array of crystalline filaments. It's a journey into materials science, into the behavior of metal atoms under stress, into processes that occur far below the threshold of human perception. Perhaps the most humbling aspect of studying whiskers is this: the exact root cause of whisker formation is still not fully understood. Despite decades of research, despite sophisticated analytical techniques and advanced computational models, the complete picture remains elusive. We know many factors that influence whisker growth. We can identify conditions that promote or inhibit their formation. We can observe them growing in real time under electron microscopes. But the fundamental question of why metal atoms organize themselves into these particular structures, under these particular circumstances, still harbors mysteries. It's a reminder that even in our age of nanotechnology and materials engineering, nature still keeps secrets at the atomic scale. What we do know with considerable certainty is that whisker growth is strongly influenced by compressive stress in the plating layer. Compressive stress is exactly what it sounds like: a force that squeezes, that pushes atoms closer together than they would naturally sit in an unstressed crystal. When metal is electroplated onto a surface, various factors can introduce compressive stress. The plating may have a different coefficient of thermal expansion than the underlying substrate, so that when temperature changes, the two materials try to expand or contract at different rates, creating stress. The electroplating process itself can deposit atoms in configurations that are slightly compressed compared to equilibrium. Intermetallic compounds forming between the plating and substrate can occupy different volumes than the original materials, again creating stress. Whatever the source, this compressive stress creates a driving force. The metal atoms in the plated layer are in a higher energy state than they would be in an unstressed condition. And nature, as always, seeks to minimize energy. Whisker growth becomes a release mechanism, a way for the stressed material to relieve pressure by extruding atoms upward and outward. The actual mechanism by which atoms move to form a whisker is fascinating. Tin whiskers grow through a process called dislocation climb. To understand this, we need to think about crystal structure. Metals are crystalline materials, meaning their atoms are arranged in regular, repeating patterns. But real crystals are never perfect. They contain defects, places where the pattern is disrupted. One type of defect is called a dislocation, essentially a line through the crystal where an extra half plane of atoms has been inserted. Dislocations can move through crystals, and their movement is how metals deform plastically. Normally, dislocations glide on specific crystallographic planes. But in dislocation climb, something different happens. Atoms migrate to or from the dislocation line, allowing it to move perpendicular to its glide plane. This process requires diffusion, atoms hopping from one position to another through the crystal lattice. In whisker growth, dislocation climb allows atoms to be added at the base of the growing whisker, pushing it upward like a slow-motion extrusion. Whiskers don't grow in random directions. Tin whiskers exhibit a preferred crystallographic orientation along the 100 direction. Crystallographic directions are specified using Miller indices, sets of numbers in angle brackets that describe specific orientations in the crystal lattice. The 100 direction represents one of the primary axes of tin's crystal structure. The fact that whiskers preferentially grow in this direction tells us that the growth process is not random, but governed by the underlying atomic arrangement. Certain directions offer easier pathways for atom movement, lower energy barriers for dislocation climb, or more favorable surface energies. The crystallographic preference is a fingerprint, evidence of the atomic level processes driving growth. When researchers examine whisker interiors using advanced techniques, they find remarkable complexity. Transmission electron microscopy shows whisker interiors contain helical dislocation tangles. Transmission electron microscopy, or TM, is a technique that fires a beam of electrons through an extremely thin sample, creating images with resolution down to the atomic scale. When whisker cross-sections are prepared and examined in a TM, the images reveal not a perfect single crystal, but a complex network of dislocations wound into helical patterns. These tangles represent the frozen history of the whisker's growth, the accumulated record of countless dislocation climb events. Each twist and turn reflects changes in stress state, growth rate, or environmental conditions during the whisker's formation. The helical structure also suggests that whiskers don't grow uniformly, but rotate or twist as they extend, driven by asymmetries in stress or crystallographic factors. The mechanical properties of whiskers are equally surprising. Nanoindentation testing reveals whisker tips are harder than bulk tin. Nanoindentation uses an extremely sharp diamond probe to press into a material at microscopic scales while precisely measuring force and displacement. When this technique is applied to whisker tips, the measurements show increased hardness, increased resistance to plastic deformation compared to ordinary tin. This enhanced hardness likely results from the dislocation structure within whiskers and from their small dimensions. At very small scales, materials often exhibit size-dependent mechanical properties. With fewer opportunities for dislocations to move and multiply in a confined volume, the material becomes harder. This hardness has practical implications. Harder whisker tips are less likely to crumble or deform when they contact another surface, making them more effective at creating and maintaining electrical shorts. The base of a whisker, where it connects to the parent surface, reveals another interesting feature. Focused ion beam milling reveals whisker roots tapered to submicron diameters. Focused ion beam, or FIB, milling uses a finely focused beam of ions to precisely remove material, allowing researchers to create cross-sections through specific features like whisker roots. These cross-sections show that whiskers don't emerge from wide, obvious protrusions, but from extremely narrow roots, often less than a micrometer in diameter. The whisker tapers outward from this tiny root, eventually reaching its full diameter some distance above the surface. This geometry provides clues about the nucleation process, suggesting that whiskers initiate from highly localized stress concentrations or grain boundary features, rather than from broad regions of the plated surface. Before a whisker becomes visible, precursors appear on the surface. Atomic force microscopy detects pre-whisker surface helix. Atomic force microscopy, or AFM, uses a tiny probe that scans across a surface, measuring height variations with nanometer precision. AFM studies of plated surfaces before visible whisker growth reveals small bumps or helix, raised areas that represent the early stages of whisker formation. These helix are sites where material is accumulating, where atoms are being pushed upward by underlying stress. Not all helix become whiskers. Some may remain as surface features, while others continue growing into full whiskers. But their presence indicates that the surface is dynamically evolving, that stress relief processes are already underway, even when no obvious whiskers are visible. When researchers collect statistical data on whisker populations, patterns emerge. Mathematical modeling shows whisker length follows a log-normal distribution. A log-normal distribution is a particular statistical pattern where the logarithm of the variable, in this case, whisker length, follows a normal bell curve. This distribution is characteristic of processes involving multiplicative random effects, where many small, independent factors combine to influence growth. The log-normal distribution of whisker lengths suggests that growth rates vary from whisker to whisker due to local variations in stress, grain structure, or other microstructural features. Most whiskers fall within a certain length range, but the distribution has a long tail extending to much longer whiskers, those rare but dangerous outliers that can bridge larger gaps. The sheer number of whiskers that can form is staggering. Whisker density can reach thousands per square centimeter. Imagine a surface area about the size of your thumbnail. Now imagine that surface covered with thousands of whiskers, a dense forest of crystalline filaments, each pursuing its own growth trajectory. Not all of these whiskers pose immediate danger. Many may be too short to reach neighboring conductors, or oriented in directions where they can't create shorts. But statistically, when you have thousands of whiskers in a small area, the probability that at least some will reach critical lengths and orientations becomes very high. The high density also means that whisker growth is not a rare, isolated event, but a widespread process affecting large areas of plated surfaces. The physical formation of whiskers represents a complex interplay of stress, diffusion, crystallography, and statistics. Atoms migrate through the crystal lattice, driven by energy gradients created by compressive stress. Dislocations climb, adding material to the base of growing whiskers. The crystal structure guides growth along preferred directions. Helical tangles of dislocations record the history of growth. Surfaces rise into helix that may become whiskers. And through it all, thousands of individual whiskers pursue their own trajectories, creating a statistical ensemble that follows predictable patterns, even though individual whiskers remain unpredictable. As we continue our exploration, we'll look at the specific conditions and materials that promote whisker growth, the catastrophic failures that have resulted, and the mitigation strategies engineers have developed. But understanding the fundamental mechanics, the atomic scale processes that turn a stressed metal surface into a whisker-generating factory, is essential to appreciating both the challenge whiskers present and the difficulty of preventing them. These are not simple corrosion products or manufacturing defects that can be easily eliminated. They're the result of fundamental materials physics, the consequence of metal atoms seeking lower energy states through the only pathway available to them. And that makes them a problem that demands respect, attention, and ongoing research. If whiskers are the visible manifestation of a problem, stress is the invisible force that creates them. Stress, in the materials science sense, is force distributed over an area, a pushing, pulling, squeezing, or stretching that deforms materials or stores energy within them. And when it comes to whisker formation, stress is not merely a contributing factor. It's the driving force, the essential ingredient without which whiskers simply don't grow. Mechanical stress from screws, clips, or thermal expansion can trigger whisker initiation. Consider the everyday reality of assembling electronic equipment. Components are mounted to circuit boards using screws that clamp them in place. Spring clips hold connectors firmly seated. Heat sinks are bolted down with significant force to ensure good thermal contact. Each of these mechanical fastening operations introduces stress into the plated surfaces they contact. A screw tightened into a tin-plated thread concentrates enormous pressure at the contact points between thread flanks. A spring clip pressing against a tin-plated shield creates a region of high compressive stress beneath the contact area. These aren't subtle effects. The stress levels can be substantial, enough to plastically deform the plating locally. And that deformation, that stress, becomes a long-term reservoir of energy that can drive whisker growth for years after assembly. Thermal expansion adds another dimension to mechanical stress. Different materials expand and contract at different rates when temperature changes. A circuit board made of fiberglass composite has one coefficient of thermal expansion. A component package made of ceramic has another. The tin plating on the component leads has yet another. When the assembly undergoes thermal cycling, heating during operation, cooling when powered off, seasonal temperature variations in the environment, these materials try to expand and contract at different rates. But they're bonded together, constrained by solder joints and mechanical attachments. The result is stress. Compressive stress where materials are forced together, tensile stress where they're pulled apart. Over hundreds or thousands of thermal cycles, these stresses can accumulate, can drive diffusion processes, can create the conditions for whisker nucleation and growth. Some material combinations are particularly problematic. Pure tin plating over copper experiences accelerated whisker growth from intermetallic formation. This is one of the most common and well-documented whisker scenarios. Copper is widely used as a conductor in electronics. Tin is widely used as a plating material for its solderability and corrosion resistance. When tin is plated over copper, the two metals don't remain separate. At the interface, copper and tin atoms interdiffuse, reacting to form intermetallic compounds, specifically copper-tin intermetallics with precise stoichiometric ratios. These intermetallic compounds occupy a different volume than the original copper and tin. As they form, they create volumetric strain. The tin layer above experiences compressive stress as it's pushed upward by the growing intermetallic layer. This process continues over time, particularly at elevated temperatures where diffusion rates increase. The result is a steadily growing stress that drives whisker formation. Many catastrophic whisker failures have been traced to pure tin over copper configurations. The electroplating process itself can introduce stress. Hydrogen embrittlement during electroplating introduces residual stresses. Electroplating involves passing current through a solution containing dissolved metal ions. At the cathode, the part being plated, metal ions gain electrons and deposit as solid metal. But other reactions can occur simultaneously. Water molecules can be reduced, generating hydrogen gas. Some of this hydrogen doesn't escape as bubbles, but instead dissolves into the freshly deposited metal. Hydrogen atoms are small enough to occupy interstitial positions in the metal crystal lattice, distorting it and creating stress. Over time, some hydrogen may diffuse out, but the stress patterns it created can remain. These residual stresses, locked into the plating during deposition, provide a built-in driving force for whisker growth. The parameters of the electroplating process matter enormously. Electrodeposition current densities above 10 amperes per square decimeter create metastable tin phases. Current density, the amount of electrical current per unit area of the plated surface, determines how rapidly metal ions are being deposited. At high current densities, the deposition happens so quickly that atoms don't have time to find their equilibrium positions in the crystal lattice. Instead, they freeze into metastable configurations, arrangements that are stable enough to persist, but not the true minimum energy state. These metastable phases may have different lattice parameters, different densities, different properties than equilibrium tin. As the plating ages, these metastable phases can transform toward more stable configurations, and that transformation creates stress, drives diffusion, and promotes whisker growth. The microstructure of the plating, the size and arrangement of individual grains within the metal, has profound effects on whisker propensity. Matte tin with grain sizes below 5 micrometers shows much higher whisker propensity. Matte tin is tin with a rough, non-reflective surface finish, typically consisting of very fine grains. When those grains are smaller than 5 micrometers, 5/1000ths of a millimeter, the plating contains an enormous density of grain boundaries, the interfaces between individual crystals. Grain boundaries are high-energy regions where atoms are not in perfect crystallographic alignment. They serve as diffusion pathways, allowing atoms to move much more rapidly than through the interior of grains. They also serve as stress concentrators and nucleation sites. A fine-grained matte tin surface has vastly more grain boundaries than a coarse-grained bright tin surface, providing more pathways for stress relief through whisker growth. The finish type matters independently of grain size. Pure matte tin finishes tend to be more prone to whisker growth. Beyond just the fine grain structure, matte finishes often have higher levels of residual stress from the plating process, more defects, more compositional variations. Bright tin finishes, which include organic brightening agents in the plating bath, tend to have larger grains, lower stress, and different microstructural characteristics that make them somewhat more resistant to whisker formation, though by no means immune. Computational modeling has helped quantify the stress levels required for whisker growth. Finite element modeling shows whisker density correlates with residual stress exceeding 200 megapascals. Finite element modeling is a numerical technique that divides a structure into many small elements and calculates stress and strain in each element. When applied to plated surfaces, these models can map stress distributions and predict where whiskers are likely to form. 200 megapascals is a substantial stress, roughly 30,000 pounds per square inch. For comparison, the yield strength of annealed tin, the stress required to permanently deform it, is in the range of 10 to 20 megapascals. So we're talking about stress levels 10 times higher than the yield strength, stress that keeps the material in a state of continuous plastic deformation, constantly seeking relief. Other material combinations create their own stress scenarios. Gold-tin intermetallic formation accelerates whisker growth. Gold is sometimes used as a plating material for its corrosion resistance and contact properties. When gold-plated surfaces come into contact with tin, either from tin-plated mating components or from tin-based solder, the two metals form intermetallic compounds. Like copper-tin intermetallics, these gold-tin compounds create volumetric strain and drive whisker formation. The problem is particularly acute in connector systems where gold-plated pins mate with tin-plated sockets, creating direct contact between the two metals. Different metals respond to different stress sources. Indium whiskers grow rapidly under compressive thermal mismatch stresses. Indium, a soft metal used in specialized solders and sealing applications, has a low melting point and a high coefficient of thermal expansion. When indium is constrained between materials with different thermal expansion rates, thermal cycling creates large compressive stresses. Indium's softness means it can't support high stress without deforming, and whisker growth becomes a preferred deformation mechanism. Indian whiskers can grow quite rapidly under the right stress conditions, reaching problematic lengths in relatively short time periods. Even alloy systems aren't immune. Hybrid tin-silver systems seed whiskers at phase boundaries. Tin-silver solders are widely used as lead-free alternatives in electronics manufacturing. While alloying tin with silver reduces whisker propensity compared to pure tin, it doesn't eliminate the problem. In tin-silver systems, the alloy consists of tin matrix with silver-tin intermetallic particles dispersed throughout. At the boundaries between these phases, between tin-rich regions and intermetallic particles, stress concentrations develop. These phase boundaries become preferential sites for whisker nucleation. The whiskers that grow from these sites can still cause failures, particularly since tin-silver solders are often used in high-reliability applications where whisker-induced failures are especially problematic. The common thread through all these scenarios is stress, compressive stress that squeezes the plated layer, that raises its energy state, that creates a thermodynamic driving force for atoms to escape through any available mechanism. Whisker growth becomes that mechanism, a release valve for stress that would otherwise have no outlet. The stressed metal doesn't flow laterally. It's constrained by the substrate beneath and by mechanical attachment to the surrounding structure. It can't simply expand upward uniformly. That would require breaking adhesion over large areas. But it can extrude localized filaments, feeding material into growing whiskers through diffusion and dislocation climb, gradually relieving stress one atomic layer at a time. Understanding stress as the fundamental driver of whisker growth provides insights into mitigation strategies. If stress is the villain, then preventing stress accumulation, providing alternate stress relief mechanisms, or using materials and processes that minimize stress become logical approaches to whisker prevention. But as we'll see in later segments, implementing these strategies in real-world manufacturing is far from simple. The same processes that create stress, electroplating, intermetallic formation, thermal cycling, mechanical assembly, are often essential to the functionality and reliability of electronic systems. We can't simply eliminate them. We must find ways to manage them, to control stress below critical thresholds, or to accept some level of whisker risk while implementing monitoring and mitigation measures. As we move forward in our exploration of metal whiskers, we'll examine specific failure cases, the testing and characterization methods used to study whiskers, and the various strategies engineers have developed to combat this persistent problem. But always, underlying every discussion, will be stress, the invisible force that transforms smooth metal surfaces into forests of crystalline filaments, the real villain in the story of metal whiskers. Metal whiskers don't grow in isolation. They exist within environments, thermal environments, mechanical environments, electromagnetic environments. And these environmental factors don't simply provide a passive backdrop for whisker formation. They actively participate in the process, accelerating growth, changing whisker behavior, and in some cases, transforming whiskers from potential threats into immediate hazards. Environmental factors such as temperature cycling and vibration can accelerate whisker growth. This statement might seem simple, even obvious, but its implications are profound. Electronic equipment rarely operates in perfectly stable conditions. Computers cycle between powered and unpowered states, heating and cooling with each cycle. Automotive electronics experience temperature swings, from freezing winter nights to scorching summer days. Industrial control systems, mounted near heat-generating machinery, see constant temperature fluctuations. Each thermal cycle expands and contracts materials at different rates, creating stress, driving diffusion, promoting the atomic movements that feed whisker growth. Vibration adds mechanical perturbations, shaking stressed surfaces, potentially nucleating new whiskers, or accelerating the growth of existing ones. The combination of thermal and mechanical environmental stresses, layered on top of the internal stresses in plated surfaces, creates a complex, dynamic situation where whisker growth rates can vary dramatically depending on operating conditions. Temperature itself has a direct effect on whisker growth kinetics. Whisker growth accelerates above 100 degrees Celsius. 100 degrees Celsius, the boiling point of water, a temperature that many electronic components routinely approach or exceed during operation. At elevated temperatures, atoms have more thermal energy. Diffusion processes speed up exponentially with temperature, following the Arrhenius relationship that governs thermally activated processes. The dislocation climb that drives whisker growth becomes faster. Intermetallic formation accelerates. Stress relief through atomic migration becomes more favorable than stress relief through elastic deformation. A component that might develop whiskers over years at room temperature could develop them in months, or even weeks if consistently operated above 100 degrees. This temperature dependence is particularly concerning for high-power electronics, for components in engine compartments, for equipment in industrial settings where ambient temperatures are already elevated. At the opposite extreme cold affects whisker growth differently. Growth slows at extreme cryogenic temperatures below negative 100 degrees Celsius. At these frigid temperatures, atoms have minimal thermal energy. Diffusion rates plummet. The atomic mobility required for dislocation climb becomes vanishingly small. Whiskers that would grow readily at room temperature may remain dormant in cryogenic conditions. This might seem like good news, a natural suppression mechanism, but it comes with a caveat. The stress that drives whisker formation doesn't disappear at low temperatures. It accumulates, waiting. If a cryogenic system is later warmed, during maintenance, during a failure scenario, during decommissioning, that accumulated stress can drive rapid whisker growth as temperatures rise into ranges where diffusion becomes feasible again. Cryogenic environments present their own unique whisker challenges. Indium whiskers pose risks in cryogenic superconducting electronics. Superconducting systems, which rely on materials losing all electrical resistance at very low temperatures, often use indium as a seal material or as a component in specialized solder joints. Indium, as we've discussed, is prone to whisker formation under stress. In a superconducting magnet system, in a quantum computing processor, in a particle detector operating at liquid helium temperatures, indium whiskers can grow during thermal cycling or from residual stresses locked in during assembly. These whiskers can bridge superconducting elements, creating unwanted electrical paths, disrupting carefully designed magnetic field patterns, or introducing resistance where none should exist. Whiskers themselves can undergo superconducting transitions. Superconducting tin whiskers lose resistance below 3.7 Kelvin. 3.7 Kelvin is negative 269.45 degrees Celsius, the superconducting transition temperature of tin. Below this temperature, a tin whisker becomes a perfect conductor, offering zero resistance to current flow. In a superconducting system, this could be particularly problematic. A whisker bridge between superconducting elements wouldn't just create a short, it would create a superconducting short, a pathway where current could flow indefinitely without dissipation. Such shorts can create persistent current loops, generate unwanted magnetic fields, or bypass critical elements in superconducting circuits. The very property that makes superconductors useful, their perfect conductivity, becomes a liability when whiskers provide unintended conductive paths. Mechanical vibration introduces another dimension of whisker-related risk. Vibration can cause whiskers to break and relocate as debris. Whiskers, despite their remarkable ability to conduct current and their enhanced hardness, are still small, slender structures subject to mechanical failure. When equipment experiences vibration, from cooling fans, from transportation, from nearby machinery, from seismic activity. Whiskers can flex, fatigue, and eventually fracture at their base. Once broken free, they become debris, loose metallic particles that can drift through an assembly. Unlike a whisker rooted to a surface, which can only create a short if it grows long enough to reach another conductor, a free whisker fragment can travel. It can be carried by airflow, can settle onto circuit boards in unexpected locations, can be drawn into connectors by electrostatic forces. A single broken whisker, drifting through an enclosure, can create shorts in multiple locations as it moves, or can lodge in a critical gap where it causes an immediate failure. The mechanical behavior of whiskers under vibration is complex. Kinked whiskers act as miniature springs under vibration. Not all whiskers grow perfectly straight. Some develop kinks, bends, or curves as they grow, perhaps due to variations in stress, changes in crystallographic orientation, or encounters with surface features. A kinked whisker has a different mechanical response to vibration than a straight one. The kink acts as a hinge point, allowing the whisker to flex more readily. Under vibration, a kinked whisker can oscillate, bouncing like a tiny spring. This oscillation can cause the whisker tip to sweep through a volume of space rather than remaining in one position. A straight whisker might need to grow to a specific length to bridge a gap. A kinked whisker, oscillating under vibration, might bridge that same gap at a shorter average length, contacting the opposite conductor during portions of its vibrational cycle. When whiskers break free, their motion can be surprisingly energetic. Whisker fragments exhibit ballistic trajectories during vibration. Ballistic motion, the flight of a projectile under the influence of forces like inertia and gravity. When a vibrating surface suddenly releases a whisker fragment, that fragment can be launched into the surrounding space with considerable velocity. The fragment follows a trajectory determined by its initial velocity, its mass, air resistance, and any electrostatic or magnetic forces acting on it. These ballistic fragments can impact surfaces with enough energy to stick, to penetrate conformal coatings, or to wedge into narrow gaps. The randomness of these trajectories means that whisker debris can appear in unexpected locations, far from where the whisker originally grew. Even electromagnetic fields can influence whisker behavior. External magnetic fields can influence whisker growth direction. This is a more subtle effect, but documented in research studies. Whiskers are electrically conductive, and in some cases, ferromagnetic or paramagnetic. A magnetic field can exert forces on the whisker as it grows, potentially biasing its growth direction. More significantly, if current flows through a growing whisker in the presence of a magnetic field, Lorentz forces can act on the whisker, creating mechanical stress that influences growth. In high-field environments, near transformers, in MRI machines, in particle accelerators, magnetic fields could potentially steer whisker growth in specific directions, making failure modes more or less likely depending on field orientation and conductor geometry. Perhaps most intriguingly, whisker growth appears to respond to long-term environmental patterns. Tin whisker growth shows seasonal variation. This observation has emerged from long-term monitoring studies of tin-plated components in various locations. Growth rates appear to correlate with seasonal temperature and humidity cycles. During summer months, when temperatures are higher and humidity levels fluctuate more dramatically, whisker growth rates increase. During winter, growth may slow in some environments or accelerate in others, depending on the specific conditions. The mechanisms behind seasonal variation are not fully understood, but likely involve the temperature dependence of diffusion, the effects of humidity on surface chemistry and corrosion processes, and possibly the influence of thermal cycling as buildings alternate between heating and cooling modes. The seasonal pattern reminds us that whisker growth is not a static phenomenon, but an ongoing process that responds dynamically to environmental changes over timescales ranging from seconds for vibration effects to months for seasonal patterns. The interaction between whiskers and their environment creates a feedback loop of complexity. Environmental conditions influence growth rates, growth directions, and whisker mechanical behavior. But the presence of whiskers can also influence the local environment. A whisker bridging two conductors changes current paths, potentially creating local heating. A field of whiskers on a surface changes its thermal emissivity, its interaction with electromagnetic fields. Broken whisker debris changes the cleanliness and reliability of an assembly. Each factor influences others in ways that are difficult to predict and nearly impossible to model comprehensively. For engineers designing electronics for harsh environments, the environmental amplification of whisker problems presents a daunting challenge. It's not enough to design for whisker-free operation under laboratory conditions. Real-world equipment will experience temperature cycling, vibration, electromagnetic fields, seasonal variations, and combinations of stresses that may never have been tested. A design that appears safe based on accelerated life testing at constant temperature might fail rapidly when subjected to thermal cycling. A component that passes vibration testing might still fail if whiskers break free during shipment and cause shorts during subsequent operation. Managing whisker risk requires thinking probabilistically, assuming that whiskers will grow, planning for debris, and implementing defensive design measures that maintain functionality even when whiskers appear. As we continue our journey through the world of metal whiskers, we'll examine specific mitigation strategies, testing methodologies, and design approaches that engineers have developed to combat this threat. But the environmental factors we've explored in this segment serve as a reminder that whiskers don't exist in isolation. They grow, break, move, and cause failures within complex, dynamic environments where multiple stresses and influences interact in ways that make prediction difficult and prevention challenging. The environment doesn't just host whiskers. It amplifies them, accelerates them, and transforms them from slow-growing curiosities into active threats to electronic reliability. When an electronic system fails unexpectedly, engineers spring into action. They gather data, analyze symptoms, examine components, searching for the root cause. But when that root cause is a metal whisker, the investigation enters a realm of frustration and complexity that few other failure modes can match. Detection and diagnosis of whisker-induced failures present challenges that can seem almost insurmountable. The most fundamental problem is this: because whiskers are fragile, failure analysis often destroys the evidence. Imagine the scenario. A critical system has failed. A circuit board is removed from service and sent to a laboratory for analysis. Technicians handle the board, turn it over, examine it visually, probe it with test equipment. Each of these actions involves contact, movement, vibration. And whiskers, these delicate crystalline filaments, can break from their parent surfaces at the slightest disturbance. A whisker that caused a short circuit might snap off during removal of the failed board from its enclosure. It might be dislodged when the board is placed on a workbench. It might vibrate loose during transportation to the analysis laboratory. By the time the board arrives for detailed examination, the smoking gun, the whisker itself, may have vanished, leaving behind only a tiny stub at its base or perhaps nothing at all. The evidence has been destroyed by the very act of trying to investigate. Even when great care is taken, the investigation process is painstaking. Failure analysis requires careful disassembly and high magnification microscopy. Careful disassembly means photographing everything before moving it, supporting boards without flexing them, cutting away enclosures rather than unbolting them, doing everything possible to preserve the spatial relationships and positions of components. High magnification microscopy means using stereo microscopes, optical microscopes with long working distances, and scanning electron microscopes to examine surfaces at magnifications from tens to hundreds of thousands of times actual size. This process is slow, methodical, and requires specialized equipment and expertise. Not every organization has access to the necessary tools. Not every failure warrants the expense and time required for such detailed analysis. Many whisker-induced failures are simply categorized as unknown cause or intermittent short, without the true culprit ever being identified. When scanning electron microscopy is employed, the results can be revealing. Scanning electron microscopy reveals dense whisker topography. The scanning electron microscope, or SEM, uses a focused beam of electrons to scan across a sample surface, generating images with extraordinary depth of field and resolution. Under the SEM, a surface that appeared smooth or at most slightly textured to the naked eye reveals itself as a landscape of whiskers. Dense forests of filaments, some straight, some curved, some kinked, emerge from the plated surface. The SEM images show not just the whiskers themselves, but their three-dimensional arrangement, their diameters, their surface textures. Some appear smooth and cylindrical. Others have nodular surfaces or show evidence of corrosion or contamination. The topography revealed by SEM provides clues about growth mechanisms, environmental influences, and the history of stress in the plated layer. More advanced analytical techniques can probe even deeper into whisker structure and formation mechanisms. Electron backscatter diffraction confirms epitaxial growth mechanisms. Electron backscatter diffraction, or EBSD, is a technique performed in a scanning electron microscope that analyzes the crystal orientation of materials. When the electron beam strikes a crystalline sample, some electrons scatter in patterns that depend on the atomic arrangement. By analyzing these patterns, EBSD can map the crystal orientation at each point on a surface. When applied to whiskers, EBSD reveals their crystallographic relationship to the parent plating. Epitaxial growth means that the whisker crystal orientation is directly related to the grain orientation of the surface from which it grew. EBSD confirmation of epitaxial growth supports models of whisker formation through dislocation climb and stress-driven atomic migration, as opposed to alternative theories involving redeposition or other mechanisms. Whiskers can even be detected through optical properties. Whiskers exhibit photoluminescence under UV excitation. Photoluminescence is the emission of light from a material after it absorbs light at a different wavelength. When some whiskers are illuminated with ultraviolet light, they emit visible light. They glow. This property can potentially be used as a non-destructive inspection technique. A circuit board illuminated with UV light might reveal whiskers as glowing filaments against a dark background, making them visible without the need for high magnification or physical contact. However, not all whiskers exhibit photoluminescence, and the technique requires specific conditions and equipment, limiting its practical application. Whisker failures can be complicated by the presence of other failure mechanisms operating simultaneously. Silver migration dendrites and tin whiskers form hybrid failures. Silver migration is a separate phenomenon where silver ions migrate across surfaces under the influence of electric fields and moisture, eventually forming conductive dendrites, branching, tree-like structures that can create shorts. When a circuit board has both tin-plated surfaces that can grow whiskers and silver-bearing materials that can form migration dendrites, failures can involve both mechanisms. A whisker might create an initial high-resistance pathway, allowing small amounts of current to flow. That current, combined with any surface moisture, might then promote silver migration, creating a dendrite that follows the whisker or forms alongside it. The resulting failure involves both crystalline whisker growth and electrochemical dendritic growth, making diagnosis complex and mitigation more challenging since preventing one mechanism doesn't necessarily prevent the other. Whiskers can defeat even robust protection measures given enough time. Whiskers can propagate through potting compounds over time. Potting compounds are polymer materials, epoxies, silicones, urethanes, that are poured or injected around electronic assemblies and then cured to form protective coatings. These compounds shield circuits from moisture, contamination, and mechanical shock. They seem like they should be impermeable barriers to whisker growth. And initially they are. But whiskers are persistent. A growing whisker encountering a potting compound doesn't simply stop. It continues to grow, applying force to the polymer. Over months or years, that constant pressure can cause the whisker to slowly penetrate the compound. The polymer may creep, developing a microscopic channel that the whisker follows. Or the whisker may push aside polymer chains at the molecular level, creating a path through the material. Eventually, whiskers can emerge on the other side of potting compounds that are millimeters thick, defeating protection that was thought to be comprehensive. The electrical behavior of whisker-induced failures adds another layer of detection difficulty. Subharmonic resonance sustains intermittent shorts. This is a subtle and insidious effect. When a whisker is on the verge of bridging two conductors, it may make intermittent contact, touching and separating rapidly. If there's vibration in the system at a certain frequency, and if the whisker's mechanical resonance is related to that frequency, subharmonic resonance can occur. The whisker oscillates at a fraction of the driving frequency, making contact periodically in a repeating pattern. This creates an intermittent short that appears and disappears with regularity, making it seem like a systematic problem rather than a random one. Technicians might search for switching noise, clock signals, or other intentional periodic signals that could explain the periodic failure, never suspecting that a mechanically resonating whisker is the true cause. Electric fields themselves can influence whisker behavior and growth. Electromigration can steer whisker growth under bias. Electromigration is the transport of metal atoms driven by electrical current. When current flows through a conductor, the momentum transfer from electrons to atoms can cause atoms to drift in the direction of current flow. In a growing whisker, if there's an electrical bias, a voltage difference between the whisker and nearby conductors, current can flow through the whisker even before it makes solid contact. This current can cause electromigration, with atoms preferentially migrating toward the positive or negative electrode, depending on the specific metal and current direction. The result is that whisker growth can be steered, biased to grow toward conductors at certain potentials more readily than toward others. This makes whisker growth patterns dependent not just on mechanical stress and geometry, but on the electrical state of the circuit, adding another variable to an already complex situation. The interaction between whiskers and operating circuits creates dynamic behavior. Tin whiskers demonstrate electrical migration during circuit operation. When a circuit is powered and functioning, currents flow, voltages are present, and electric fields exist between conductors. A whisker growing in such an environment experiences these electrical influences. Atoms within the whisker or on its surface can migrate under the influence of the electric field and current. This migration can accelerate whisker growth towards certain conductors, can cause whiskers to bend or change direction, or can modify the whisker's structure and composition over time. The whisker is no longer just a passive structure responding to mechanical stress, but an active participant in the electrical environment, with its growth and behavior coupled to circuit operation in complex ways. All of these factors, the fragility of evidence, the need for specialized analysis equipment, the slow and painstaking nature of proper investigation, the presence of hybrid failure mechanisms, the ability of whiskers to defeat protection measures, the complex electrical and mechanical behaviors that create intermittent or unusual symptoms, combine to make whisker detection a nightmare for failure analysts. Many whisker failures are never properly diagnosed. They're written off as one-time anomalies, as unexplained intermittent problems, as component infant mortality. The true scope of whisker-induced failures may be far larger than documented cases suggest, simply because many failures are never investigated deeply enough to reveal the whisker culprit. For organizations trying to understand reliability issues in their electronics, this detection difficulty has serious implications. Without proper diagnosis, the same failure mode can repeat. Replacement components with identical plating and stress conditions will develop whiskers, just like their predecessors. Preventive measures can't be implemented if the root cause isn't recognized. Warranty costs accumulate. Customer satisfaction suffers, all because the microscopic evidence of the failure, the tiny whisker that bridged two conductors, was too fragile to survive the investigation process or too subtle to be found without specialized techniques. As we continue exploring the world of metal whiskers, we'll examine the mitigation strategies that have been developed, the standards and guidelines that industry has established, and the ongoing research seeking to finally solve this persistent problem. But the detection challenges we've discussed remind us that addressing whisker failures requires not just prevention, but also the capability and commitment to properly diagnose failures when they occur, to invest in the analysis tools and expertise needed to find these microscopic culprits, and to share that knowledge broadly so that the entire industry can learn from each failure and gradually build more robust, whisker-resistant systems. The theoretical dangers of metal whiskers are concerning. The microscopic mechanisms are fascinating, but nothing drives home the seriousness of this phenomenon quite like examining the real-world disasters that whiskers have caused. These aren't laboratory curiosities or hypothetical scenarios. They're actual failures that disrupted services, endangered lives, cost billions of dollars, and in some cases, changed the course of technology development. One of the most visible whisker-induced failures in modern history occurred in 1998. Tin whiskers disrupted pager service across the US during Galaxy 4 failure. Galaxy 4 was a communications satellite owned by PanAmSat, orbiting in geostationary orbit above the equator. On May 19, 1998, the satellite experienced a catastrophic failure of its primary control processor. Backup systems were supposed to take over, but they failed as well. The satellite tumbled out of control, its antennas no longer pointed toward Earth. Within hours, approximately 45 million pages across the United States went silent. Doctors couldn't be reached. Emergency services lost contact with first responders. News organizations couldn't communicate with field reporters. The economic impact was measured in hundreds of millions of dollars per day. Investigation eventually revealed that tin whiskers had created short circuits in the control system electronics. A satellite that cost hundreds of millions to build and launch, that was supposed to operate reliably for 15 years, was brought down after less than 3 years of operation by crystalline filaments measuring micrometers in diameter. Transportation systems have been particularly vulnerable to whisker-induced failures. Zinc whiskers caused Swiss railway signaling failures in the 1970s. Switzerland's renowned railway system, known for its precision and reliability, began experiencing inexplicable signaling problems. Signals would show incorrect aspects. Track occupancy detectors would malfunction. Switch points would fail to respond to commands. Engineers investigating these failures discovered zinc whiskers growing on relay contacts within signaling equipment. The relays, housed in equipment rooms along the rail lines, used zinc-plated contacts that had been in service for years. Compressive stress from repeated switching operations, combined with environmental conditions, had triggered whisker growth. The whiskers created phantom circuit closures, causing the signaling system to perceive conditions that didn't actually exist. Given that railway signaling is a safety-critical application where failures can result in collisions, derailments, and loss of life, these whisker-induced malfunctions represented a serious threat to public safety. National security infrastructure has not been immune. Whiskers shorted missile control systems at NORAD, the North American Aerospace Defense Command, responsible for monitoring airspace and coordinating defense responses to potential threats, experienced a system outage in 2003 that was traced to tin whiskers. Control systems for missile warning and tracking, systems that absolutely must function reliably during a crisis, were compromised by microscopic metal growth. The incident occurred during a period of heightened security awareness following the September 11th attacks, making the failure particularly alarming. Investigation revealed tin whiskers on circuit boards within control system hardware. The whiskers had created shorts that caused processors to malfunction, taking down portions of the missile control network. The failure forced a comprehensive review of electronics throughout NORAD facilities and prompted broader Department of Defense efforts to address whisker risks in military systems. Space exploration has suffered repeated setbacks from whisker-related problems. Cadmium whiskers delayed NASA's early spaceflight program. During the Mercury and Gemini programs of the 1960s, when America was racing to achieve human spaceflight milestones, cadmium whiskers were discovered in critical relay systems. Cadmium plating was widely used at the time for its corrosion resistance and low friction properties. But in the space environment, with its vacuum conditions and temperature extremes, cadmium proved prone to whisker formation. Relays that controlled thruster firing, life support systems, and communications equipment developed cadmium whiskers. Some failures occurred during ground testing, allowing problems to be corrected. But the constant threat of whisker-induced failures added uncertainty to mission planning and forced costly inspections and component replacements. The delays and additional costs associated with addressing cadmium whisker problems set back timelines and consumed resources that could have been directed toward other aspects of the space program. Medical device failures carry particularly grave implications. Tin whiskers shorted medical device electronics. Pacemakers, implantable cardioverter defibrillators, insulin pumps, and other life-sustaining medical devices have experienced whisker-induced failures. A pacemaker malfunction can result in a patient's death if the device fails to deliver properly timed electrical pulses to maintain heart rhythm. An insulin pump failure can lead to diabetic ketoacidosis, a life-threatening condition. The FDA has documented multiple instances of whisker-related failures in medical devices. The low-power electronics in these devices, with their closely spaced circuit traces and long operational lifetimes, create ideal conditions for whisker-induced shorts. Patients implanted with these devices trust them completely, often unaware that microscopic metal filaments could compromise the electronics that keep them alive. Medical device manufacturers have had to implement rigorous whisker mitigation strategies and conduct extensive reliability testing, but the risk cannot be entirely eliminated. High-speed rail systems in Japan have also experienced whisker-related incidents. Whiskers caused emergency braking failures in Japanese bullet trains. The Shinkansen, Japan's famous bullet train system, operates at speeds exceeding 300 km per hour. At these speeds, braking systems must function with absolute reliability. Any failure that prevents proper braking could result in catastrophic derailments or collisions. In several incidents, whiskers were found to have created electrical faults in braking control circuits. The high-reliability electronics used in these systems, with their conformal coatings and sealed enclosures, were supposed to prevent such failures. But whiskers grew nonetheless, eventually creating shorts that compromised braking system functionality. The incidents forced extensive inspections of Shinkansen rolling stock and modifications to electronics designs to reduce whisker susceptibility. Power grid infrastructure represents another critical system vulnerable to whisker failures. Whiskers have triggered cascading grid failures. Electrical power grids are complex, interconnected systems where a failure in one component can propagate, causing other components to fail in a domino effect. Aluminum whiskers on high-voltage bus bars, zinc whiskers on relay contacts in substations, tin whiskers in protective relay electronics. Any of these can initiate faults that trip circuit breakers, reroute power flows, and potentially overload other parts of the grid. Cascading failures can black out entire regions, affecting millions of customers, shutting down critical infrastructure like hospitals and water treatment plants, and causing economic losses measured in billions of dollars. While not all grid failures are whisker-related, documented cases exist where whiskers were identified as the initiating event that triggered a cascade. The information technology sector has discovered that whisker problems can emerge after long periods of apparent stability. Whiskers have caused server farm outages after years of dormancy. Data centers housing thousands of servers, providing cloud computing services, hosting websites, and processing business-critical applications, have experienced sudden outages traced to whiskers. In some cases, the affected equipment had been in operation for 5, 7, or even 10 years without problems. Then, suddenly, servers began failing, network switches crashed, and storage systems locked up. Investigation revealed tin whiskers on circuit boards, connector contacts, and other plated surfaces. The whiskers had been growing slowly for years, finally reaching lengths sufficient to bridge critical gaps. The long dormancy period is particularly troubling because it means equipment that has passed initial burn-in testing, that has operated reliably for years, can still fail catastrophically due to whisker growth. No operational history, no matter how long, guarantees future whisker-free performance. In the harsh environment of space, whisker behavior can be especially destructive. Whiskers have welded adjacent conductors in spacecraft. When a whisker bridges two conductors in the vacuum of space, and when sufficient current flows through that whisker, the whisker can heat rapidly. There's no air to carry away the heat through convection. The whisker may vaporize, creating a plasma arc as discussed in earlier segments. That arc, carrying high current in the vacuum environment, can generate temperatures high enough to melt the conductors themselves. The molten metal from both conductors can fuse together, creating a permanent short circuit, essentially welding the conductors into a single piece. Unlike a temporary whisker bridge that might be cleared by the whisker breaking, a welded short is permanent and irreversible. The affected circuit is destroyed, and if redundancy isn't available, the spacecraft function is lost forever. Perhaps most concerning is the persistence of whisker problems despite decades of awareness and mitigation efforts. Whiskers continue to appear in modern high-density electronics. Smartphones, tablets, laptops, automotive electronics, industrial control systems, telecommunications equipment, all continue to experience whisker-induced failures. Modern electronics actually face increased whisker risk in some ways. Component density is higher than ever, with circuit traces spaced mere micrometers apart. Operating temperatures are elevated due to higher power densities. Lead-free soldering, mandated by environmental regulations, has replaced lead-bearing solders that were less prone to whisker formation. The RoHS Directive, restriction of hazardous substances, eliminated lead from most consumer electronics, forcing manufacturers to adopt pure tin or tin-rich finishes that are inherently more susceptible to whisker growth. While mitigation strategies exist, none are perfect, and the economic pressures of consumer electronics manufacturing often prioritize cost reduction over long-term reliability. As a result, whisker problems persist, causing warranty returns, field failures, and customer dissatisfaction. These real-world disasters span decades, span industries, span applications from space to medicine to transportation to telecommunications. They demonstrate that whisker formation is not a niche problem affecting only specialized applications. It's a broad systemic threat to electronic reliability across virtually all domains. Each failure teaches lessons, sometimes at enormous cost. Each investigation adds to our collective understanding. But the continued appearance of whisker-induced failures, even in modern systems designed with awareness of the problem, shows that we have not yet solved this challenge. Metal whiskers remain a persistent threat, a ticking time bomb hidden within countless electronic systems, waiting for the right combination of stress, time, and environmental conditions to trigger their growth and cause the next disaster. As we move forward in our exploration, we'll examine the mitigation strategies that industry has developed, the standards and testing protocols that have been established, and the ongoing research seeking more effective solutions. But these real-world disasters provide essential context. They remind us why whisker research matters, why prevention efforts are crucial, and why engineers must remain vigilant against this microscopic, but potentially catastrophic threat to electronic reliability. For decades, engineers have known about the whisker threat. They've documented failures, studied growth mechanisms, and worked to develop countermeasures. The fight against metal whiskers has been ongoing, evolving, and marked by both successes and setbacks. Some mitigation strategies are remarkably effective. Others introduce new problems or prove impractical for widespread implementation. Understanding these approaches, their benefits, their limitations, and their trade-offs, is essential to appreciating the complexity of managing whisker risk. The most effective whisker suppression method discovered to date is elegantly simple. Adding 0.5 to 3% lead to tin suppresses whiskers. This small amount of lead alloyed into tin dramatically reduces whisker formation. The mechanism isn't completely understood, but several factors appear to contribute. Lead atoms in the tin lattice may interfere with dislocation climb, the fundamental mechanism of whisker growth. Lead may also affect grain structure, producing larger grains with fewer grain boundaries to serve as diffusion pathways and nucleation sites. Additionally, lead may reduce the compressive stress that develops in tin plating, either by accommodating strain through different mechanisms or by modifying the mechanical properties of the alloy. Whatever the exact mechanism, the practical effect is clear. Tin lead plating, particularly the traditional 63% tin, 37% lead eutectic composition, showed dramatically lower whisker propensity than pure tin. For decades, this alloy was the standard finish for electronic components and circuit boards, providing reliable, whisker-resistant surfaces. But this effective solution was taken away by environmental concerns. RoHS restrictions removed lead, reviving whisker risk. RoHS, the Restriction of Hazardous Substances Directive, was implemented by the European Union in 2003 and subsequently adopted or mirrored by regulations in many other jurisdictions. RoHS restricts the use of lead and several other substances in electrical and electronic equipment, driven by concerns about environmental contamination and human health impacts from improper disposal of electronics. The directive forced a massive transition across the global electronics industry from lead-bearing to lead-free materials. For soldering and surface finishes, this meant switching from tin lead to pure tin or tin-rich alloys. Almost overnight, the industry lost its most effective whisker mitigation tool. The result was predictable: a resurgence of whisker-related failures. Equipment that would have been protected by tin lead finishes now uses pure tin and experiences whisker growth. The environmental benefits of lead elimination must be weighed against the reliability costs of increased whisker risk, a complex trade-off with no simple answer. Without lead as an alloying element, engineers have turned to other strategies. Nickel underlayers reduce stress and diffusion. Rather than plating tin directly onto copper, a thin layer of nickel is first deposited on the copper substrate, and then tin is plated over the nickel. Nickel serves multiple functions. It acts as a diffusion barrier, preventing or greatly slowing the formation of copper-tin intermetallic compounds that create stress. Nickel has different mechanical properties than copper, and the nickel layer can accommodate some stress that would otherwise be transmitted to the tin. The nickel underlayer approach has become one of the primary whisker mitigation strategies in the lead-free era. It's not perfect. Whiskers can still grow on tin over nickel, but the risk is significantly reduced compared to tin directly on copper. For the most demanding applications, more exotic finishes can provide superior protection. Gold plating over nickel provides whisker-free finishes. Gold does not form whiskers under normal conditions. By plating gold over a nickel underlayer, manufacturers can create surfaces that are essentially immune to whisker formation. The nickel provides a stable substrate, and the gold provides a whisker-resistant surface. This approach is widely used in high-reliability applications, aerospace, military, medical devices, where the additional cost of gold plating is justified by the criticality of reliable operation. However, gold plating is expensive. Gold prices fluctuate, but typically range from tens to hundreds of dollars per troy ounce. Plating costs, including the gold material itself and the process complexity, make gold-plated components significantly more expensive than tin-plated alternatives. For consumer electronics, where cost pressures are intense, gold plating is generally not economically viable. Another precious metal can provide similar benefits at somewhat lower cost. Palladium underlayers act as stress buffers. Palladium, like nickel, can serve as an underlayer beneath tin, providing diffusion barrier properties and stress accommodation. Palladium has the advantage of being directly solderable, meaning tin solder will wet and bond to palladium without the need for an additional finish layer. Some manufacturers use palladium-nickel alloys as underlayers, combining the benefits of both metals. While palladium is expensive, though typically less so than gold, the quantities required for thin underlayers are small enough that the cost premium may be acceptable for high-reliability applications. Thermal treatments can provide temporary relief from whisker growth. Annealing at 150 to 200 degrees Celsius can delay whisker growth. Annealing is a heat treatment process that allows atoms in a material to redistribute, relieving internal stress. When tin-plated components are heated to elevated temperatures for extended periods, typically several hours to several days, compressive stress in the plating can be partially relieved through thermally activated stress relaxation mechanisms. The tin atoms have enough thermal energy to rearrange themselves, finding lower energy configurations that accommodate the stress without requiring whisker formation. Annealing doesn't eliminate the underlying causes of stress. Intermetallic formation continues, new stresses can develop, but it can significantly delay the onset of whisker growth, buying time before mitigation becomes critical. The limitation is that annealing is an additional process step, adding cost and cycle time to manufacturing. It also exposes components to elevated temperatures that may not be compatible with all materials and assemblies. Physical barriers can contain whiskers even if they don't prevent their growth. Conformal coatings thicker than 25 micrometers can encapsulate whiskers. Conformal coatings are polymer layers applied to circuit boards to provide environmental protection. When these coatings are thick enough, they can physically contain whiskers, preventing them from extending beyond the coating layer to contact adjacent conductors. 25 micrometers, 25 thousandths of a millimeter, is thick enough to encapsulate typical whiskers and provide mechanical restraint that may limit their growth. However, as we've discussed previously, whiskers can sometimes penetrate even thick coatings over extended time periods. Conformal coatings also add cost, weight, and process complexity. They can trap heat, reducing component cooling effectiveness. And they make rework and repair more difficult, since accessing components requires removing the coating. Surprisingly, inducing the right kind of stress can actually help prevent whiskers. Rotary abrasion introduces beneficial tensile stress. Whiskers grow in response to compressive stress. If tensile stress, pulling rather than pushing, can be induced in the surface layer, it opposes whisker formation. Rotary abrasion involves mechanically working the plated surface, perhaps through controlled buffing or polishing operations. This mechanical work can introduce tensile stress in the near-surface region. The tensile stress counteracts any compressive stress, reducing the net driving force for whisker growth. The challenge is controlling the process to achieve consistent tensile stress without damaging the plating or introducing other defects. Chemical treatments can modify the interface between plating and substrate. Zincate immersion layers reduce intermetallic stresses. Zincate treatment involves immersing components in a zinc-bearing solution that deposits a very thin zinc-rich layer at the interface between the substrate and the subsequent plating. This zinc layer can modify the formation of intermetallic compounds, potentially reducing the stress they create or providing a sacrificial layer that accommodates stress. The effectiveness of zincate treatments varies depending on specific materials and processes, and they add complexity to the plating process. Some engineers have explored electrical methods for managing whisker risk. Periodic high-voltage conditioning pulses can fuse incipient whiskers. The concept is to intentionally apply voltage pulses that are higher than normal operating voltage to circuit boards during testing or periodic maintenance. If small whiskers have begun to form, these pulses may cause them to carry enough current to fuse, to vaporize and clear themselves before they grow long enough to cause persistent shorts. It's a form of controlled failure, eliminating small whiskers before they become large problems. The risks are obvious. The conditioning pulses could damage components, could create other failure modes, or might not consistently clear all whiskers. Implementation requires careful design of pulse parameters and comprehensive testing to ensure the treatment doesn't create more problems than it solves. Each of these mitigation strategies has found application in specific contexts. High-reliability aerospace systems might use gold over nickel plating combined with annealing and thick conformal coatings, multiple layers of protection despite the high cost. Consumer electronics might rely primarily on nickel underlayers and perhaps thin conformal coatings, accepting some residual whisker risk in exchange for lower manufacturing costs. Military systems might specify lead-bearing finishes under exemptions to RoHS regulations, prioritizing reliability over environmental concerns for mission-critical applications. But none of these approaches is perfect. None eliminates whisker risk entirely. Even gold-plated components can experience failures if whiskers grow from other plated surfaces in the assembly. Nickel underlayers reduce, but don't eliminate whisker formation. Conformal coatings can be penetrated. Annealing only delays growth. And many mitigation strategies conflict with other design objectives: cost reduction, miniaturization, thermal management, manufacturability, environmental compliance. The fight against whiskers is ultimately a risk management exercise. Engineers must assess the criticality of the application, the acceptable failure rate, the available budget, and the manufacturing capabilities, and then select a combination of mitigation strategies that provides adequate protection given these constraints. For some applications, the conclusion might be that whisker risk must simply be accepted, with reliability margins designed to tolerate occasional failures. For others, exhaustive mitigation measures are justified regardless of cost. As we move toward the final segment of our exploration, we'll look at the future, at ongoing research, emerging technologies, and the long-term prospects for finally solving the whisker problem. But the mitigation strategies we've examined in this segment represent the current state of the art, the tools available today for fighting back against metal whiskers. They're imperfect tools, but they're what engineers have to work with as they struggle to build reliable electronics in a world where microscopic metal filaments constantly threaten to create the next failure, the next disaster, the next costly lesson in the persistence of this invisible threat. After decades of whisker-related failures, after billions of dollars in damages, after countless hours of research and investigation, the scientific community continues to search for better solutions. The cutting edge of whisker research represents hope. Hope that we might finally develop materials, processes, and designs that eliminate or dramatically reduce this persistent threat. The approaches being explored range from subtle modifications of traditional plating chemistries to radical new fabrication techniques, from computational prediction tools to active intervention strategies. One of the most promising directions involves finding alternatives to lead that provide similar whisker suppression. Bismuth additions suppress whiskers as a lead-free alternative. Bismuth is a heavy metal that sits near lead in the periodic table and shares some similar properties. Research has shown that adding bismuth to tin in concentrations similar to those used for lead, a few % by weight, can significantly reduce whisker formation. The mechanisms appear similar to those of lead, involving interference with dislocation mobility and modification of grain structure and stress states. Bismuth has the crucial advantage of being far less toxic than lead. While bismuth compounds aren't completely benign, they don't carry the same level of environmental and health concerns that drove the elimination of lead through RoHS regulations. Bismuth tin alloys could potentially provide whisker resistance approaching that of traditional tin lead finishes, while remaining compliant with environmental regulations. However, bismuth additions affect other properties of the plating. Melting temperature, solderability, mechanical strength, and extensive testing is required to ensure these alloys perform adequately across all the requirements for electronic finishes. Other researchers are exploring the use of dopants, trace additives that modify plating properties at very low concentrations. Antimony trisulfide dopants pin dislocations. Dislocation pinning is a metallurgical concept where small particles or impurities in a crystal prevent dislocations from moving. Since whisker growth depends on dislocation climb, the movement of dislocations through the crystal lattice, pinning those dislocations can inhibit or prevent whisker formation. Antimony trisulfide, when incorporated into tin plating at trace levels, creates pinning sites that interfere with dislocation motion. The dopant particles are small, nanoscale in some cases, but their presence throughout the plating layer creates a distributed network of obstacles to dislocation movement. The challenge is incorporating these dopants uniformly during electroplating and ensuring they remain stable over the lifetime of the component, rather than dissolving, agglomerating, or diffusing away over time. Some of the most dramatic whisker reduction results have come from rare earth elements. Rare earth elements like cerium reduce whisker density by 95%. 95% reduction is an extraordinary improvement, transforming whisker formation from a common occurrence to a rare event. Cerium and other rare earth elements, added to tin plating in small quantities, appear to fundamentally alter the stress state and microstructure of the deposit. The exact mechanisms are still being researched, but the practical results are compelling. Components plated with cerium-doped tin show drastically fewer whiskers in accelerated life testing and long-term monitoring. The obstacles to adoption include the cost and availability of rare earth elements, which are subject to supply chain constraints and price volatility, and the need to modify established electroplating processes to incorporate these additives without creating other problems. Process modifications can be as important as material changes. Pulse electrodeposition produces near-zero stress coatings. Traditional electroplating uses constant direct current to deposit metal. Pulse electrodeposition instead applies current in pulses, short bursts of current separated by periods of no current, or even reverse current. This pulsing allows the deposit to relax between pulses, reducing the buildup of residual stress. The ions in solution have time to organize themselves more optimally before the next pulse arrives. The result can be plating with dramatically lower stress than continuous plating at the same average current density. Near zero stress means there's no significant driving force for whisker growth. The plating remains stable over time, with stress levels too low to trigger the dislocation climb mechanism. Pulse plating requires more sophisticated power supplies and process control than traditional constant current plating, adding cost and complexity to manufacturing. But for critical applications, the reliability benefits may justify these additions. Entirely different fabrication approaches are being explored. Pressureless sintering produces whisker-resistant finishes. Sintering is a process where metal powder particles are heated to temperatures below their melting point, causing them to bond together through solid-state diffusion. Pressureless sintering means this is done without applying external pressure. The powder is simply heated in a controlled atmosphere. The resulting finish has a different microstructure than electroplated metal. The grain structure, stress state, and defect distribution are all different. Research has shown that sintered tin finishes are significantly more resistant to whisker formation than plated finishes. The porous nature of sintered coatings might also provide internal volume that can accommodate stress without requiring whisker extrusion. However, sintered finishes have different surface properties than plated finishes, different roughness, different solderability, different appearance, and may not be suitable for all applications. Thin film deposition techniques offer another avenue for whisker-resistant coatings. Sputtered tin films resist whiskering below 1 micrometer thickness. Sputtering is a physical vapor deposition process where tin atoms are ejected from a target by ion bombardment and then deposit onto the substrate. Sputtered films have very different characteristics than electroplated films. They're typically very uniform in thickness, have fine-grained structures, and can be deposited with controlled stress states. Research has found that when sputtered tin films are kept below 1 micrometer in thickness, 1/1000th of a millimeter, they show greatly reduced whisker formation compared to thicker films or electroplated coatings. The limitation is that such thin films may not provide adequate corrosion protection or solderability in harsh environments, and they're more easily damaged by handling or abrasion. Active intervention strategies propose to eliminate whiskers after they've begun growing. Laser annealing selectively melts whisker tips. High-powered, precisely controlled lasers can be scanned across a surface, delivering enough energy to melt the tips of any protruding whiskers without damaging the underlying plating or components. The molten whisker material resolidifies, ideally forming a ball or bump rather than regrowing as a whisker. This could potentially be implemented as an in-service maintenance procedure, periodically laser treating critical assemblies to clear any whiskers that have developed. The challenges are substantial. Detecting whiskers to know where to aim the laser, delivering precise energy doses that melt whiskers without causing other damage, ensuring the treatment is effective across different whisker sizes and orientations, and doing all this economically at scale. But the concept represents creative thinking about whisker management beyond simply trying to prevent formation. Computational tools are becoming increasingly sophisticated at predicting whisker behavior. Quantum simulations predict whisker nucleation sites. Quantum mechanical simulations model the behavior of materials at the atomic scale, calculating how individual atoms interact, how they'll arrange themselves under various conditions, how defects will form and evolve. Applied to whisker formation, quantum simulations can examine grain boundary structures, analyze stress states around defects, and predict where whisker nucleation is most likely to occur. These predictions could guide manufacturing process optimization, help identify which batches of components are at highest risk, or inform inspection strategies that focus on the areas most likely to develop whiskers. However, quantum simulations are computationally intensive. They can only model very small volumes of material for very short simulated time periods. Bridging from quantum simulations at atomic scales to predictions about real components operating over years remains a significant challenge. At larger scales, finite element modeling continues to advance. Finite modeling correlates stress gradients with whisker density. As discussed in previous segments, finite element analysis can calculate stress distributions in plated surfaces. Researchers are now correlating these calculated stress fields with observed whisker densities from test samples and field failures. By mapping where whiskers actually grow and comparing that to predicted stress patterns, models can be refined and validated. The goal is to reach a point where stress modeling can reliably predict whisker risk for a given design, allowing engineers to modify geometries, change materials, or add mitigation measures before components are manufactured. This predictive capability could dramatically reduce the trial-and-error nature of whisker-resistant design and catch problems in the design phase rather than discovering them through field failures. Despite all these emerging approaches, current consensus suggests that comprehensive protection requires multiple defensive layers. Multi-layer barrier systems provide the most reliable long-term defense. Rather than relying on a single mitigation strategy, a special alloy, or an underlayer, or a particular process, the most reliable approach appears to be combining multiple techniques. A typical multi-layer system might include a nickel or palladium underlayer to prevent intermetallic formation, tin plating with bismuth or rare earth dopants to suppress whisker growth in the tin itself, thermal annealing to relieve residual stress, and a conformal coating to physically contain any whiskers that do manage to form. Each layer provides partial protection. Even if whiskers partially defeat one layer, the others provide backup defense. This defense in-depth approach is expensive and complex to implement, but for the most critical applications, life support medical devices, flight control systems, nuclear power plant instrumentation, the cost may be justified by the near elimination of whisker risk. The future of whisker research will likely continue along multiple parallel paths. Materials scientists will seek better alloys and dopants. Process engineers will refine deposition techniques. Computational researchers will develop more accurate predictive models. Design engineers will create circuit layouts and component geometries that are inherently less susceptible to whisker-induced failures. Standards organizations will update guidelines and requirements based on accumulating field experience and research results. And failure analysts will continue documenting whisker-related failures, feeding lessons learned back into the research and development cycle. What's certain is that metal whiskers will remain a concern for the foreseeable future. The fundamental physics that drives whisker formation, stress relief through dislocation-mediated mass transport, won't change. As long as we use electroplated metals in electronic assemblies, as long as those assemblies experience stress from thermal cycling, intermetallic formation, and mechanical constraints, whiskers will continue to grow. The question is whether we can manage the risk to acceptable levels through better materials, smarter processes, more comprehensive mitigation strategies, and deeper understanding of the mechanisms at play. For anyone working with electronics, whether as a designer, manufacturer, reliability engineer, or end user, awareness of the whisker threat is the first step toward managing it. Understanding that these microscopic metal filaments can grow silently over years, eventually causing catastrophic failures, should inform design decisions, material selections, inspection protocols, and maintenance strategies. The cutting-edge research we've explored in this segment offers hope for better solutions, but those solutions are still being developed, still being validated, still working their way from laboratory demonstrations to commercial implementation. As we conclude our journey through the world of metal whiskers, from their discovery in 1940s era vacuum tubes to the latest quantum simulations and rare earth dopants, several themes emerge. Whiskers are persistent. They've plagued electronics for 8 decades and show no signs of disappearing. They're unpredictable. The same materials and processes can produce whisker-free components or whisker-infested failures with no obvious pattern. They're dangerous, capable of bringing down satellites, disrupting critical infrastructure, and compromising life-saving medical devices. And they're challenging. Despite intensive research, we still don't fully understand all the factors that control their formation, and we don't have perfect solutions for preventing them. But we've also learned that whiskers can be managed. Through careful material selection, process control, design practices, and mitigation strategies, whisker risk can be reduced to acceptable levels for most applications. The research at the cutting edge promises even better tools for fighting this microscopic threat. And every failure, every investigation, every research paper adds to our collective knowledge, gradually building toward a future where metal whiskers become a solved problem rather than an ongoing crisis. Until that future arrives, engineers will continue their vigilant watch, designers will implement defensive measures, manufacturers will control their processes, and researchers will probe ever deeper into the atomic-scale mechanisms that transform smooth metal surfaces into forests of crystalline filaments. The battle against metal whiskers continues, fought on microscopic scales, but with consequences that echo through the largest systems humanity has built. It's a reminder that in our technological world, the smallest threats can sometimes pose the greatest dangers, and that understanding and respecting those threats is essential to building the reliable, robust electronics our modern civilization depends upon.